перекладача, а ми надамо з перекладом на YouTube-каналі. Це трохи займе у нас часу. Ну, знаючи, як це подає Branimir, я думаю, що вам буде зрозуміло і англійською мовою. So, Branimir, I have to go, but
yes, okay.
I wish you good day, good luck, good lecture.
Okay.
And, you can
Thank you
start.
very much. Thank you very much for arranging everything. Okay.
Yeah. Bye-bye.
Bye. Bye. But Vika, hello?
Да, я тут.
How many?
Мы можем начинать, Branimir.
But how many participants are now in?
Now you have 13 participants, but you can start, then they will join us. Okay, Branimir?
Should I wait a little bit more, or?
No. They will join us, and we have the recording of this lecture.
Okay.
Then it will be posted on YouTube channel, and they can start from the very beginning. Okay. Thank you.
Okay.
Bye.
Okay, thank you. Okay, that was I was confused. Okay, just give me a minute and then I start. Hello, good day or good morning. For those who are lately coming in, I am welcoming you to the IPL web presentation, which is designed, or I'm invited by Michael Bratach, and thanks to him, he devoted some of his time to this fantastic learning process in a time when we are in the middle of the crisis of Corona. So this today's talk is on multi-fructured horizontal well production. I thought when I was asked to give a presentation, what I'm going to really present, based that I know UGV and based that I know all the problems. I didn't want to interfere in anything what was related directly to the UGV workflow. I have some of the opinion, which is mostly based on the low quality data we have in UGV, but anyhow, this is not the subject today of my talk. My talk is oriented to the future for UGV, that is shale gas, tight gas. That is why I'm presenting semi-analytical solution for a multi-fractured horizontal well, which is one of the options we should consider when we will be making production scenario of the new assets we will have in UGV. I'm still feeling like that I'm UGV, so I'm telling we instead of you will have. So basically, as you see, I have one horizontal line and I have 1, 2, 3, 4, 5, 6 fractures. The very first presentation is related to the gas field. And as I mentioned, my approach is screening approach. Screening approach means that it is fast approach. Fast means that I have solutions which are extremely fast. And what are that solutions? These solutions are semi-analytical solutions. So what kind of semi-analytical solutions we are using in the UGV today? These are all Kappa Sapphire solutions, partly also Topaz solutions, partly the empirical, partly analytical. And then Rubis is the only one which is numerical one. So what that means, I have certain data and I have a pretty fast model. Fast model means you have to ask yourself, what does it mean fast? Is it heterogeneous? Yes, it is heterogeneous. Is it multi-phase? No, it is not multi-phase, it is single phase. Then, so I have monophase model. What that means model? Do I need capillary pressure curve? No. Do I need relative permeability curves? No. So that means what I need. So once you have a well testing, you know that you have only certain number of parameters which are related to the reservoir, to your well, and then they are related also in this case, because we are talking about fracture, to the fracture. So these are the three main items which we have to put into the reservoir. Of course, we have to consider reservoir temperature and pressure. So this is practically the main input you should have. So where we are with analytical solution on this graph, for example, you can see that cost of the performing study is on X, Y, Z, and on YZ you have accuracy and of an answer and applicability. So what does it mean? Of course, if I'm using numerical model, I'm more accurate. I'm emulating. I'm never 100% accurate. I'm always emulating Mother Nature. Realistic model is always much more complex than any model. Then analytical model is simplification, but if we know how to use it, then it may be valuable. Most of the time, at least on the Western side, when in the oil company I used to work, they start with something what is mostly analytical or empirical. So basically, I want to understand the concept of what is going on with my asset or with my reservoir. So in this case, I'm using the most simplest tools. And then, of course, I'm adapting certain data which is going to honor that simplicity. And then I'm going to get some understanding of the processes. And then I'm going to dig into more data. While I'm digging into more data, I'm increasing more numerical approach. So now, what is analytical? What is numerical approach? When we talk about a numerical approach in making fractures, we may use finite element methods. But when we are talking about numerical model in flow simulation, we are talking about finite differences. This technology is developed from 80s on, so that is well developed now for over 40 years. When it comes to analytical, we are still on diffusion-based equation. So that means we have to make scenario. I need to have inner boundary condition and outer boundary condition. Inner boundary condition are constant pressure, constant rate, or variable pressure, variable rate. In well testing, we know that the pressure is always constant rate. And pressure is an answer. Analysis of derivative plot of pressure, build-up, for example, I can have well response, I can have reservoir response, and I can have no flow boundaries. Until I will reach the no flow boundaries, in between it is pseudo-steady state point, and that point is ending transient flow to the no flow. So no flow boundary. So basically with this scenario, that is well testing. In rate testing, we have also quite the same. We have pseudo-steady state point. And in this pseudo-steady state point, what we have is really, we differentiate something what is depletion and something what is transient. But this depletion part is further modeled by the ARP's empirical equations. So that means I'm going to use analytical diffusion-based solutions in order to solve multi-fructured horizontal well. So here my inspiration comes from the North Sea. you can see here that I have all field in the North Sea. And the greenish, the green part is remaining unexploited reservoir according to current plans. These are, Ekofisk is one of the biggest and troll field in the North Sea. Norway is producing 200, we're producing at the very beginning, almost for 20 years, 200 million tons. So that would be, let's say that UGV today is producing 20 million tons of equivalent oil. That will be 10 times more. But the population of the nation is 4.5 million. That means that they are producing per year 100 times more than you. So with this, you can imagine this 100 when you multiply by 40 years, that is enormous income to Norway based on raw oil and gas production or hydrocarbon production. So you can see here that I have, first of all, produced oil is what is gray here. Then the dark green is remaining, planned to be production. So that is not so much left, but still we have the remaining unexploited reservoirs. That is something what probably you have the same in Ukraine. You have unexploited reservoirs and you have the leftovers which we have to put in Yablanovka, I don't know, all other field, Berezovka, Kotelve. So that is what your target is to target this dark green, but then that must be that you explore more asset and investigate by have better seismic, so you will be digging into the remaining unexplored reservoir. So this is basically, as you see in the North Sea, everything, all the wells are drilled from one template, drilling template, and you see how they looks like on the subsurface on the sea. And most of the well have the wellhead at the bottom of the sea. So that is now maybe more than 50% of the wells have the template at the bottom of the sea. That is differentiation to the continental offshore. So another what motivated me was that instead of having horizontal well, instead of having, vertical well with fracture, and then I drill, let's say 1, 2, 3, 4, 5, 6 vertical wells, and these drawings, I put one horizontal and make transversal fracture. What we will now explain in a minute, what means transversal, what means longitudinal. So first of all, I would like to come back to the main graph, which is really following always all well production. And that is the graph made by Cvetkovic on rate, pressure, time. On the left side, you have transient response. On the right-hand side, you have no flow boundary response or bounded reservoir response. So basically, my analytical solution today to be presented to the audience, because I presume that I'm going to use the horizontal multi-fructured well in a tight reservoir. That means this well will stay in a transient mode for long, maybe for 1, 2, 3, 4 years. So it depends on the permeability of the reservoir, on the quality of the reservoir. Thus, I'm using transient solution. Another way would be to calculate time PSS, that is the middle point here, which differentiate my transient response to the, on Cvetkovic type curves, to the empirical flow, no flow boundary curves. So first of all, we have to look at the fracture orientation when we drill the well. Does your formation suggest the horizontal direction to be located parallel to the maximum stress or minimum stress? And then, of course, we can see here the differentiation that the transversals is perpendicular to the minimum stress, and the longitudinal is in a line with the maximum horizontal stress. So basically, as we see here, the way how we position, we have to understand the rock mechanics. And that is must when we have such complex scenario as making horizontals with fractures. In addition to that, we do need to have very high quality seismic, because usually we can have maybe not more than, let's say, 20 meters of the height of the pay zone. And in this 20 meter, we have to follow the trajectory of the well, and then we have to make the fracture stages on that. So here is once again, I am here, as you see on the transversal, I am perpendicular to the minimum stress. And here I am, in this case, you can say that, I am perpendicular to the minimum stress. So that is why to the longitudinal fracture. So the fracture. So that means that I am along with the maximum productivity. So now another parameters so that means we have to understand what is longitudinal, what is transversal fracture. Then we have also to understand what is infinite conductive fracture, what is finite conductive fracture, and what is FCD, that is dimensional fracture conductivity. So the dimensional fracture conductivity, that is usually when I have a fracture with a certain width, is really multiplication of the permeability of fracture with that width. Width is omega, and then divided by the half length of the fracture. So that means indication of F is K fracture, and X is my half length of the fracture. And this half length has to be multiplied by K formation, and here I have fracture K multiplied by omega fracture, and here I have half length of the fracture multiplied by K. So on both sides, I have dimension of omega and X in feet, for example, and K is square foot. So that means I see that this is my dimension is FCD. Once again, fracture permeability and fracture width divided by formation permeability and fracture half length is fracture in dimension is fracture conductivity. So that is the most important parameter we need to understand and to have. So now I have again scenario with 3 fractures. The first one are transversal, and then the second one are longitudinal. So I'm going to ask you, what is really horizontal well? From the fracture point of view, it is really, you can say, as I see it, I will say, okay, let me put that fracture, longitudinal fracture, so small that the height is the radius of the well, then that is really what is my horizontal. That is the most simplification I can have. So basically, because I can have very long fracture, let's say in this case I have to put that the fracture is long, let's say 200-300 meters, and the height of the fracture is only radius of the fracture height. So now I have to go to my presentation summary. What about the screening analysis? We want to estimate optimal number of fractures. This is my first objective, because usually if UGV is going to drill the well, the operator will say, okay, we will drill certain number of fracture, but we don't know which one we should drill. Or usually they drill how many fracture they prognose that they should have, but no one make prediction of the production profile. Several times I was approaching Amerada Hess and other operating company in that time by developing this software. I will tell you later on more how this product was made and who did it. And no one was interested in coupling this valuable tool to something what can be beneficial to the operator. So that means that means you just think you build a house and it has 8 floors. And then the company which is building flats, they say, oh, maybe we will make 6, it depends on the quality of the base or whatever. And then earthquakes. So basically, you don't know. So that is what is going on with those who are doing fracturing. So you have to be sure, at least when you are following the scenario on the field, to make some kind of the prognosis why you are drilling certain number of fractures. So let's say, I'm talking now about Clipper South, UK asset. When I was in biogas, we used to have about 100 assets, and one of the assets was tight reservoir, gas tight reservoir, and they were drilling horizontal well with a certain number of fractures, and then they said it would be 8, for example. Then I wanted to make the model explaining why these 8 fractures should be really made. So in addition to that, I wanted to assess the productivity of the created fracture, and then I wanted to detect the difference in fracture production for propan fracs and acid fracs. So that is also quite important, because what means propan fracs and what means acid frac? Propan fracs really means that I'm introducing the fracture conductivity to the fracture system. Otherwise, I'm using infinite conductivity. You remember, you noticed at the very beginning, we explained what is the difference. The difference is here, there is that in infinite, there is no pressure drop, and in propan, there is a pressure drop. So that is very important to differentiate. And then that means you have to know which, when you say, oh, I'm going to use acid, I'm not going to use the propan solution, I have to use acid solution, or vice versa. So then on another side, what was achieved that also 8 fracs can be justified, and with based on the cutoff on cumulative gas production, and then further achievement that we have to verify everything by using more sophisticated data, or like PLT data. These data are usually normal procedure and must in the North Sea. And unfortunately in Ukraine, we are still trying to introduce this technology into the portfolio of the exploration or development. So the lower objective is, that means to evaluate optimum number of transversal fracture on the horizontal well, to prognose the fracture horizontal well productivity, and then to assess the productivity. And further, in order to achieve that, we are using screening analysis of the multi-fructured horizontal well. As I mentioned, Clipper South is an asset in UK, and semi-analytical model is named HOWIF. And that model I initiated and I created, and it is part of ended as a part of my PhD work. I was very lucky when working in Institute for Energy Technology, that is Norwegian, very reputed institute, which made Olga simulator. Olga is a transient pipeline simulator. And this simulator is a must tool once you will be having any asset in the Black Sea, because once you have in the deep of water, undulating pipeline. That means you will have accumulation of water and you have to see the pressure stations, how much pressure you have to use in order to push the water, otherwise your pipeline will be blocked. So that means in a cross section of the pipeline, in each place in time, I know how the phases changes. Then we have to estimate gas production profile. Okay, so I didn't finish that. I work at the Institute for Energy Technology, and one of my project proposal was when I went to Philips Petroleum Company that operate Ekofisk, to Viggo Holm. He was chief reservoir engineer, Norwegian guy. And he asked me, okay, you bring us proposal for the horizontal well study, but we would like that you make the research project developing multi-fructured horizontal well. And they say, can you make a proposal that we need horizontal well with 100 fractures, can you make it? So in order to start the project, I went to mathematical conference in Saint-Étienne. That was conference on theory of filtration. We made a poster. And then I got discussion with very many mathematicians. And at that point, I realized that it would be worthwhile to start the project. So now in Norway, when you are a research institute, you have to go out and beg for the money. But with the brain, you have to write proposal. So that means you write proposal, we want money to make this and this. And then, of course, you have a big sharks who are smarter than you are. So you have to be very clever how you are presenting yourself and what you are doing. Smarter means that they can pay, company can pay whomever they can, and the best of the best. So I met Martin Luylands, the guy, the BP guy, chief guru in fracturing. So he was interesting to have such a tool. I was just explaining before why. So what I did then, I said, okay, here's proposal. And then he saw my name and he said, oh, did you publish SP paper on condensate blockage with Economides? I say, yes. Okay, here's $100,000, like this. I got a check for $100,000. Then I went to Konokov, then I went to BP, so then I get $1 million in 3 years research. With $1 million, I managed to make a team of over 5 people, which put into over 10 man-years of work. And we managed to make the probably best software. In my next lecture, I will show how it works in that time. So the only one more thing, in order to convince that we are competent, I have to go to Oklahoma, to Bartlesville, and to convince Raj Raghavan. I would like to know if those who were lecturing well testing are aware of that name, Raj Raghavan. Raj Raghavan is probably one of 3 best well test guys. Well testing and rate testing. So this software is both pressure well testing software and rate testing software, because solutions are based on inner boundary condition of pressure and rate. So I can switch one to another. I can get pressure response when I put a rate constant, or a rate response when I put pressure constant. So based on that, Raghavan said, oh, we are also making the same tool, but we are willing to pay you $300,000 in 3 years. So we will see what we can gain under one condition, that we get your source code. So we provided them source code, but anyhow, this was the pay, the price. So now what we did further, with this software, we can estimate gas production profile for various number of fractures. That means with different fracture height, half length, and fracture conductivity. So there is a lot of option inside which can make variation of the fracture. I want to say in the time when we were developing software, LGR was under development. It was not yet implemented. So that is why this software was valuable in that time. But when I was defending the thesis, then Leif Larsson, who is developing all Kappa and Sapphire solutions, even, and he is now 77, and he's still software development. He is probably one of the best mathematician Norwegian, and he was my first opponent when I defended my thesis. The another one was also from Stanford University. This one is, he's from US, but also he's Norwegian, Finnish Oslo University, mathematics. And the first one, that was the guy who was leading my project, was also from a postdoc from Stanford. That is Jon Steinar Gudmundsson, who passed away, unfortunately, 3 years ago when I was on my way to Ukraine. So I'm just putting this name because without their support and without my communication with them, I think I will not be handing to this what is done. So the final statement here is to provide workflow for future modeling study of a horizontal well with transversal fractures. So that is my well horizontal, and as you see here, you have 1, 2, 3, 4, 5, 6, 7, 8. Why 8? Why not 7? Why not 5? Why not 10? That was my question. So you just think, you have now time. I got the data on Friday and I delivered the report on Monday morning. Do it with Petrel. Or whatever. One only competitive software which was made by Soliman. That is also another story. I will use my opportunity not to promote, but also to put you through very big names. I was fortunate to meet them. He was the Halliburton guy, and Halliburton investing in his research, and he made a quick look software simulator, let's say for tight or for gas. They have fantastic gas solution, but without fracture model. So I said, okay, let us compare solution. I have analytical model and we make comparison of my answers and your answers. Huh? We got different answers. Why? Do you know why? When he was making grid around this, emulating my transient response, this grid along this fracture was just on the tip of the fracture. So it was too small. The direction was too small. When you need to make transient simulation, you need to make big area because you don't know what is your drainage areas. Otherwise, you are going to have a pot model, and that is not what is a bounded reservoir. What is transient? Transient needs space. It's a wave which goes. It's free wave. So based on that, that was the first. Another solution was, which I will explain more when I came to Cvetkovic curve, which I use Larsson and Hegre solution. The Larsson is the guy, as I mentioned, who is now Leif Larsson, who is now developing software together with Olivier in Kappa engineering. He's one of the most senior guy and very good mathematician. I want to say that Olivier, both Olivier, there are two Oliviers in Kappa engineering, the main boss and the vice president, they are Stanford University. Then there is in a rank, the first rank at Stanford University is Remy. The second one is Alan Gringarten. I used to work with Alan Gringarten. The third one is Raj Raghavan. I was 3 years with Raj Raghavan involved in work. And then life Larsen is the fourth one, which I really respect highly. You have now, of course, new players, but this is what you have to remember, at least this name, and you have to know that these names are somehow connected to this the work here. So here is the fracture placement. Of course, when I'm going to make analytical model, I'm not going to now make all parameters which are like this, because I am assuming that my well is horizontal, so I can somehow make the medium height of this fracture and make that all fractures are equal. Okay. So let's say, so what you have here, your horizontal well, usually your well is really like this. So of course, by making some kind of the model which is like above here, I can say that is like this one here. I can see that maybe these are my fractures, but I'm not so sure that I have to be very precise. Anyhow, I have to check how precise is my measurements. And that is the biggest problem. Usually people don't put any error in petroleum engineering, as in physics, in measurements. So that is, you have to make assumption. And then my question is, if we are not going to use analytical solution, then why we are doing well testing? Why we are doing well testing? Any answer? Because you have three-phase flow and well testing is monophase. In well testing, you don't have relative permeability curves, no capillary pressure curves. Why we need the well testing then? But we need, because you have to compare with something and to understand better. Because with well testing, I can see the faults, I can see all multi-layering, I can make all kind of characterization of the reservoir, which I could not simply see in Eclipse or any flow simulator. So again, this is it is to repeat, it is power engineering tool. I mean, some analytical model. I am making potential drainage profile, which can view the impact of the well performances. Further represent way for having screening view towards achieving production estimate. And the use of detailed G&G and flow modeling is more accurate, but it is time consuming and it's costly. We all know that. So model design, finance was given by BP, ConocoPhillips, Norwegian Research Council and Institute for Energy Technology with $1 million and with 10 years of work. The company, and I was project initiator, project lead, and project executive. So Raj Raghavan, Viggo Holm, Bijan Agarwal, Regatos, Martin Rylance, Chris Dyke, Bill Landrum, and then Ken Kosko, Christian Sørensen, and Leif Larsen. So as you see, all these were those who were participating during the project work. So you see, in the Norway, when you do such a work, particularly if you have, if your institute is reputed, you are coupled to industry. And this is obligation of UGV, and this is then respond to the university. Otherwise, you are not going to develop university environment, and you will not do anything what you need. And research is must for any petroleum company. You can always out-resource research, but you have to have guru who know and understand what they're doing. As I mentioned in my previous lectures, be engineer, not technician. So, only. So, model assumption in this approach is that I have height of the reservoir, I have 8 fractures with a certain height of the fracture and half length of the fracture. Now I have to deal with this, what is conductivity. So now I have fracture permeability, I have fracture width. And then I have on a side permeability of the formation. And I have also the width of the formation. So basically, these are the basic parameters which I need to have in order to control or to have a solution of this, what I'm going to model. But the main issue is here, how I'm going to couple well with fracture to the reservoir. And the next question is really how a simulator do that. Okay, so what we have when we have coupling of the well to the reservoir. Then we should have the well, which is positioned in a grid block. And this grid block has assume, because of the different size of the well radius and the grid block, we have a scaling problem. So we have somehow to solve and emulate that for each of the phases, I am using Pisman radius. I'm not using three-phase Pisman radius. So this Pisman radius is a simplification. Why? Because it assumes that it's an analytical solution. And it is also very important that we understand this solution, that the flow around the well is radial. But what if the flow is not radial? Or are you going to say that once you have a fracture is going to take the fluid or gas from around, and then that your flow around the transfers of fracture are going to be radial? I'm not so sure. So how you are going to deal with that? That is interesting. That is very interesting how you solve it. That is why ideally numerical simulator should be compared to analytical one, that we know what is differentiation. It doesn't mean that we should be equal, but we will, if we are highly off, then we know that something is wrong with the solution. So now I have Wellbore. I have to know how long is Wellbore. I have to know where if I have a direct flow to the Wellbore, because I have the flow through the fracture. You know, first what I have, fracture is the opening. So my fluid is going to go to the fracture, and then over the fracture to the point, and this point would be quite critical because I may have a choking effect here. So this is also have to be modeled, by the way. And then in between, I can have closed path or direct flow to the Wellbore. So you have to include in your solution direct flow to the. So that means I have direct flow to the fracture. Then through fracture, I am directly connected to the Wellbore. On another side, in between, I have no flow or direct flow to the Wellbore. And that all combined comes into one solution. So now I have half length, that is fractures, half length, that means fracture height, that is this, what you can see here, but how is length? Length is here. So half length, are they equal or unequal? I'm using now equal, but I can easily make unequal. And then making an investigation, I will show you my SP paper where I made a lot of studies showing you, and you will see and digest how nicely you can understand the modern nature of the, because you could not do that very quickly with Eclipse. You can do it when you are experienced, but if you are unexperienced, it will take you a long time and you will be completely confused. So, or you will not have time for that because you will need to make something else for your boss and you will never finish that. Then I have length, a length which can be equal or unequal. Then fracture conductivity, which will be uniform flux, infinite conductivity, and finite conductivity. Infinite, we are using mostly when we talk to the chemistry, to the infinite, no pressure drop, and finite conductivity that is pressure drop. When I put propan, then means I keep width. In order to keep width, you have to know that the price in between making infinite to finite conductivity is 10 times difference. It's extremely costly for oil company, and no one wants to do that. Usually they will always end up with a acid stimulation. Only sometimes that you sacrifice money and put into the finite conductive. And at least in the North Sea, in chalk ecofisk. Then penetration has to be fully penetrated and partially penetrated. So that means I have a height. So that means if this is my height of the reservoir, I can be here or I can be up to the taking hole reservoir. Usually I think when I was talking with our expert team with Bilic in UGV, usually they go for 6-meter fracture. So let's say if they have a zone of 20 meters, they are pretty pleased, and they are going to do the fracture when it's 6-meter half length penetration of the fracture. So that means fracture is partially penetrated because presume that I have 20 meters of the zone. So then I have with the 6-meter partially penetrated fracture. Fully penetrated means that I have 20 meters. Reservoir parameters, it's pretty easy. Like in well testing, well-bore, fracture, reservoir, or you have well-bore and reservoir, and some other fluid parameters are very basic. Initial pressure, height, viscosity, compressibility, formation volume. So what we are going to do, we are going to assume that there is no pressure drop here in the wellbore. We can make pressure drop, but in this case, I put no pressure drop. And then I use formation volume factor to put my reservoir Brelle to the surface with this. So that is how you end up with the production. So now how it looks like. So I have here different type of models. Slab means that I am cutting the reservoir. And that means, let's say that I cut the reservoir at a certain height that is 100 meters. That is my slab. And then I can have field units and metric units. My initial conditions are constant pressure, variable pressure can be also rectangular or elliptical, fracture shape. Then in this case, I'm using rectangular fracture shape. Then in a boundary condition of constant pressure, variable pressure, and constant rate and variable rate. Then I can have a transversal fracture and longitudinal fracture, but I have in parallel all solution for everything. Then I have no flow boundary, constant pressure boundary. And then I have the upper part, and then I have at the lower part, no flow boundary, constant pressure boundary. And then I have fracture penetration, we explained that, fully penetrated, partially penetrated. So now I'm coming to uniform flux. Usually, as I said, we are using finite conductivity. It's more academic. Uniform flux, it is a bit, but finite conductive is propan, and the infinite conductive is when I have acid injection. So with this, I am using, in this case, fracture width and fracture permeability. And we know that fracture permeability is huge compared to the reservoir. This is normal because that is why fracture is. So fracture is really how I see fracture is a plain wellbore. I don't know, ukrainski, valjda ravnina, svedlovina ravnine. Ravnina svedlovine, probably, I don't know. So half length is, you have to emphasize the number, but if it is equal spacing, if it is unequal, you just put the row of data, how many, it depends how many fractures you have. And then you can also equally put equal spacing or unequal spacing. And in addition to that, so that was the first was half length, and then it was the height, fracture height. In this case, I'm using partial penetration, otherwise it will be fully penetrated, will be, as we said, 20 meters. And then what is nice, I have to include also choking effect. Skin and storage, they were in that time under development. So now I put next, and then I come to the, if I want to have single well or multiple well, and then I can also make, if it is multiple, I want to put well length, and then I want to get out a certain report. Now I'm coming to the time scope. Time scope means I have to put, like in flow simulation, I have to put delta t. What is the time I am going to from to? So now, of course, I don't have time step. Why do I not have time step? Because it's not final differences. Final differences means that I have discretization of space and discretization of time. Here I don't have that. Then I have Velbor friction, that is interesting. And I have also option direct flow to the Velbor. So you remember that first we talk about choking effect. That is when I have well penetrating perpendicular or longitudinal fracture. Of course, the all flow at that point is going to the Velbor within the fracture. So then I will face choking effect, which I have to simulate. And then I have also to introduce Velbor friction and even more direct flow to the Velbor. You know, up to now, in between two fractures, I have a pipe that is my Velbor, and there is no inflow to that pipe. But if it is like open hole, then I will have inflow. So then I have to emulate that. Now I come to the reservoir. In the reservoir, I have initial pressure. I can also put upper and lower boundary pressure, but in this case, I'm using initial pressure. I can put reservoir thickness, horizontal permeability, vertical permeability, porosity, and total compressibility. It's easy because I have only one fluid. It's monophase. Then I have viscosity and formation volume. And then I come to the numerical method. So what that means numerical method? This is parabolic partial differential equation first, and it has solutions in space and time. Diffusion equation in all well testing is usually solved in such a way that I have dimensionless rate and dimensionless pressure versus dimensionless time. The whole secret of dimensionless is that Q dimensionless is equal constant, which is physics mu constant. I will put that KQ, multiply Q, and then the P. And that is for all three. That is for Q, that is for P, and that is for T. With this, I can put, that is hidden but never shown in type curves, plot it, and then I can calculate something what is K, and K is usually, you derive from K permeability and you derive skin from K. In addition of that, you can use from type curves, for example, drainage radius, and that is, you have 3 parameters which control your characterization of the reservoir with this such simple model. At least this is principle of transient rate testing and transient pressure well testing. So with this, that means in order to solve this equation, I have to go from parameter xt to xz. Z is complex variable. It's not z xyz, it is z is complex values. And sometimes use s, but I don't want to do s because s will confuse me with the scheme. So now, when I have, let's say that I have two equation with 2 unknowns, that is x and t. I'm not able to solve it. In order to solve it fast and quick, I come to Laplace space where I have x and z Laplace variable, and then when I have found solution for x, this x can be, in this case, if it is constant pressure rate, my rate, then I have to go back by using Steffes algorithm, which is going to bring me, it will going to put back Q and return my time t. So that is basically the whole what is this Steffes doing. And interesting, it's not done by mathematician. I think the guy was I think he was economist, and he was making gambling in Monte Carlo. So he found a very good solution for that. And by coincidence, the first guy who used that algorithm was Sandal. He was a master's student at Stanford University, Norwegian fellow, and he used this Steffes algorithm. Now you have at least 50 different algorithms, but Steffes is one of the most robust. I will show you that it can explode, and I will show my presentation today. You will see what that means. So, study objective was to make a fractured horizontal well Clipper South study to estimate optimal number of fractures. The target was 1 million standard cubic meter per day of a horizontal well with 8 fractures. And then to assess the productivity of created fracture and to predict various fracture type gas production. That is propan fracs, acid fracs. Okay? So you see, this is answer of cumulative gas production versus time. And you can see that I have for one fracture, that is the line on the bottom. First of all, then that is the cumulative for one fracture. Cumulative for 2 fractures, number 2 is here, it's 2, 3, 4, 5, 6, 7, 8, 9.
10.
Hello? So this is cumulative. On another side, I have a rate versus time.
1, 2, 3.
From 10,
7.
1. Okay? So
Yes.
basically you can see here that my one fracture is quite low. 2 fractures are quite well producing reservoir. Then 3 fractures are even more bringing. 4, 5 is probably okay. And then I have to investigate somehow when I have to make cut, when I'm not really, the question is is this cumulative production, which was on the previous one, this difference in between the last one and the 9 one and the previous one is going to pay the one fracture. If economically this will pay, we will move up, up, up with the number of fractures. If not, then we are going to go down, 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 okay?
Yes, да.
So gas rate versus time is just the same. Cumulative is more showing because cumulative is really what you are producing. Rate is nothing. Even it will be better that I plot productivity index because even rate is not the best indicator of any production. Productivity index is the only indicator because it comprises pressure drop, it gives rate. Here you don't see pressure drop. So here is my then cumulative gas production after certain time. So that means you can see that how much one fracture, second, third, after that time is 1600 days. And these are the propan fracture. And here is the, it's just the same, sorry. The same. I have several the same, but anyhow. Now here I have cumulative gas. So you can see here that I have now one fracture, second fracture, third, fourth, fifth, sixth, seven, and so on. So you can see that here I'm not so sure that this difference is going to pay the frac, that frac. The question is now, is this difference here is going to pay that frac? Maybe this difference is going to pay that frac. See?
Yes.
So based on that, you can say, you see, you plot the differentiation of the cumulative, and then you investigate what is the percentage your one frac is producing, second frac, third frac, fourth frac, fifth, sixth, seven, 8, 9, and 10. And then you can see that in the matter of fact, 9 and 10 are really not bringing too much. So that means 8 may be justified as a good number of fractures at a certain length of the fracture. So this is then cumulative production.
I like
Please exclude because I don't know, you are interrupting. I don't know who is commenting. So now I have cumulative gas versus.
Sorry, Branimir. Андрей и Родион, пожалуйста, выключите свои мікрофони, ви немножечко мешаєте. Або задайте свої питання. Sorry, дякую.
So here is my income frac. You know, I calculated what is income per number of fracs. And then you can put here fracture numbers. You can then put certain, that is NPV value, how you calculate. So study objective was really to fracture horizontal well, to estimate optimal number of fractures, to target certain production. That would usually be in an OC plateau production, and then of course is going to be after some time under decline. To assess the productivity of created fractures and to predict various fracture type, gas production, propan fracs, and acid fracs. And optimal number of fracs was 8, fracturing cost, and fracture conductivity of 2% per. So with these numbers, you can be, that is one way to calculate, you know, I'm not an economist, so there are those who are probably more involved in economy evaluation of the fracs, but this just to show that one semi-analytical tool can make quick screening decision before any final decision by management is made. So now I'm looking at the horizontal well with 8 propan fractures. And, you can see here, that is interesting. What is going to be here? You have here, you can here set a number of fractures. So how many of these curves you have here at the bottom? Okay, how many curves you should have? That is my usually, when I make the exam for the students, because I was lecturing almost in my career, almost, I don't know, maybe 15 years altogether. I was lecturing in petroleum summer school 7 years. At the University of Lorraine in France, I was lecturing fractured reservoir for 5 years. I was also 2 years at KPI in Ukraine, and also 3 years at University in Zagreb, and also was in Brazil and Almaty, Kazakhstan, at Al Farabi University. So basically, my students' question to University of Lorraine was how many, why I have down, not see, I have 4 fractures, 4 curves, cumulative, and the last one is well production, total well production. That is why it is so big, okay? Why I have 4? That is the question for those who are participating. Can anyone answer? Okay, so if we go back, you just put one line. Can you see when I'm putting this on the screen or not? No. I don't know how to introduce this program. No, it doesn't. Ah, excellent. Okay. So when I have here 1, 2, 3, 4, 5, 6, 7, 8. My drainage radius is here, big, and here is big, okay? And that is this line here. Is it clear? Because I'm aside of the well. Well is in a huge reservoir. The wire is wide. Can you follow me? Then this one here is this one here. And then I have this one. This one is this one below. And finally, I have that one, and that one, which is this one here. So I have here 4, that would be 1. Okay, so that would be 1, 2, 3, 4, 5. This one would be 4 and 5. Four and 5. This one is 3 and 6. The next one is 3 and 6. And then the next one is this is 2 and 7. And finally, green is 1 and 8. Okay? And this one is sum of Q I from 1 to 8. Okay? So what should I do now? Huh? Yes. Okay. Okay. Now it's the question how I move that. Okay. Yes. Okay, now it's done. So now I would like to go further. So I have now cumulative gas versus time production. So now I have 3 propan finite conductivity fracture. Of course, when I have 3, I have only at the bottom. You could not see that number 1 and 3 is number 1 and 3 are on the top. So this is 1 and 3, and this one is 2. So when I count this plus this is here, and then I come to the cumulative overall production. So that means this is cumulative well with fracture, and this is only fracture. So what means that these rates are differentiated? That means that I have proper model. Proper model can be also emulated by finite differences, but if you ever have any software, you have to check that. I know that in Eclipse it is possible to add some kind of the evaluation of the fracture rate, not directly like here I have, but in that case, we have to be sure that this is honoring basic interference. Otherwise, you are using analytical solution which are wrong, because you are really putting solution which are the same solution at each rate based on the height and the half length of that, but you are not using interference and proper draining of the area around the fracture. And here I have finite conductive fractures, the same. Now I'm only plotting 2 because 1 and 3 are the same, and in the middle is squeezed, that is the line on the bottom. Here I have uniform flux fractures. again, I have here uniform flux fractures, which are number 1 and 3. See? And here is just the same. So basically, I am able to of course, the case is ideal. I am not able to use this module for undulating well. Undulating well means that it is not horizontal. But then you have to introduce a trajectory, you have to introduce gridding, you have to be sure and that the way how fracture are coupled to the well bore are honored or mathematically solved for the best. I presume that Eclipse and those commercial software like CMG has the best solution, but even these solutions are not equal and will never be equal. You will never have the same solution of the simulator, any simulator. For that, you have to look at the SPE comparison studies 1 to 10, which were also initiated by Khalid Aziz from Stanford University, when they put the same input data, provide this data to the company and the companies, and then they provide their solutions. And you can see the differentiation. No, you can be recognized. It's visible. It's not invisible, it is visible. So, to repeat, after estimated number of fractures with a certain target, we assess the productivity of fractures that were really made. And then, in addition, we made an efforts to put differentiation in between propan and acid fracs. Acid fracs, of course, are pretty good, but you know, the propan frac is costly, but it lasts longer. And acid frac is more cheaper, and it doesn't last long. And in addition to that, you will see later in my next hour presentation that what can be done further with this module. So I suggest that we have 5 minutes break. Is it okay? Hello? 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 Can you hear me? Hello? No one is listening anymore. So now I will continue. So here is the propan frac and acid frac differentiation. You invest, but you get more. And that is also cumulative propan frac and acid frac for 3 fracs. For horizontal well with 3 fracs.
Как-то он идет в твою сторону, не трогай меня.
Алло.
О, боже мой, это будет опасно. Такого не надо превращать.
Юлія Гума, будь ласка, виключіть свій мікрофон. Дякую.
My final comments would be like this. Study results may be used for better estimation and understand of a horizontal well with fractures. both propane and acid, future production. Study assess the productivity of fractures in both type, and the obtained results has to be verified by the commercial software or gas simulator. What was done? I told you that it was verified by quick look. And the model should be further tested with the PLT data, and screening study comprises output generated with which is generated a semi-analytical model made from a multi-fructured horizontal well in oil reservoir. So oil and gas reservoir. So now how you can really use, once you have liquid solutions, how you can use these solutions for gas? This is my question to those who are reservoir engineers. Let's say I have a liquid solution software, and I have a gas field, and I would like to use this solution to the gas field. What I'm going to do? Think about that. So now my final notes to what is done in this first presentation. We have a semi-analytical monophase liquid model. Fractures are transversal, and each is equally spaced and has equal fracture length. Unequal fracture spacing and unequal fracture half-length option is not presented in this study. A series of full-time solutions corresponding to various conditions are given in a multiple fracture horizontal well model, based on the input which you were presented. So you see all kind of combinations what you can have in the model. Then model limitation, we don't have non-Darcy flow. We don't have also pseudo pressure should be considered instead of reservoir pressure, PI and PWF. So that means I'm answering the question I stated. If I put pseudo pressure instead of my liquid pressure, I can use that for gas flow. Model was tested. That would be my next presentation with Clipper South, and in the next presentation with Valhall, Norway, and South Arne from Denmark. That was the field operated by Amerada Hess. The field has only multi-fractured horizontals. Further, the model results were verified first by the analytical solution of Leif Larsen and Hegre, then by well test 200, that was Schlumberger well testing software, which is now moved. I believe strongly most solutions are now moved to GeoQuest Schlumberger software. Further, by quick look Halliburton software, which is made by Mohammed Soliman. And well test 200 I worked together with Raj Benarrier from Abingdon office in Schlumberger. Afterwards, Raj Benarrier together with Mike Tabenyahu made great software, which was multiple well software used as a semi-analytical DCS software tool. But in the time when I worked for Schlumberger, they never had multi-fractured horizontal well solution. They asked me for my solution, and of course I didn't share that for nothing. So, as I said, further model needs some justification by more data, like PLT data for horizontal fractured well. And it has been verified by both oil and gas reservoirs. And these are donors here at the bottom, which are early. So I also mentioned that Steffes may cause some problems by moving from, whenever you get such response from your analytical solution in well testing or whatever software tool that use Steffes or any other algorithm, you have to tune parameters in that algorithm, and then you avoid this noise, as here you see. This will tell you, it may be also that you have non-linearity, but that will not be shown because the software will be stopped or it will crash. Here, the software is not crashing, but it tells you, okay, I have to do something with tuning parameters. So it's direct note to those who have to tune parameters for Steffes algorithm. That you have to change only one parameter, that is number of iteration. In this case, I'm using 8 divided by 2, which is 4. Otherwise, you can go to 10 or to 12. If you use more, it will explode again. So that is just for those who are doing. What is the beauty of having knowledge how to perform such study? It is really that we can take from the literature any Laplace solution formula and put that in a software which is going Steffes, and then you will have response. So if you find in the literature solutions based on only one parameters, it's space parameter, that is distance, and S complex variable, you can use that solution, use Steffes, and get a real production number. So just be aware of that. And I must honor Miljenko Simic, your colleague, who is not anymore, unfortunately, with UGV. As I know, he was the only one in UGV who was doing that. If I'm wrong, I will be happy. So, relevant literature to that is effective Elbor parameters productivity of a multi-fructured horizontal well. And I have been going on different conferences. One of them was in all kind of the SP papers I had, and the thesis, which is talking much more of transient and no flow boundaries flow. So this thesis is really, this is the last paper, which is made in Oklahoma. When I went to the conference, and then I went to the lunch with Michael Economides. Thanks to this guy, I managed to move from a long time ago from Croatia to Ukraine, to Norway, because I was, we published together the paper on condensate blockage, which I presented in Den Haag at Europec SPE. And then Professor Jon Steinar Gudmundsson from Stanford, he was a just new employee at the University of Trondheim, offered me 3-year scholarship of Philips. So that is how I moved to Norway. That was exactly 30 years ago. So now, what is the beauty of this analytical module? That you can make some kind of characterization of the fractures. I have presented several responses of fracture cumulative and fracture rates. But now the question is, can I make simplification instead of having 3 fractures? Let me make just like, okay, you know that when you're using skin, what you're doing, you're increasing your radius, equivalent radius of your well, or decreasing. With stimulation increasing, because you have E over minus S. So when S is negative, it is positive, and when S is positive, it is negative, so it decreases radius. So skin decreases, but negative skin increases radius. So that is the measure of skin. So here, I want to see the measure of productivity of horizontal well with 3 fractures. Then I put number of fractures. I put what is my radius of fractures, and then I want to calculate for 1 fracture what is my equivalent radius. Okay, and then I want to calculate from 2 fractures, for 3 fractures, what is my equivalent radius. So based on that, and also in the same time, I want to calculate what is my half length. So basically these parameters, in this case, I'm calculating equivalent radius, you see, for 2 fractures. And then also I'm calculating equivalent. So from here, I'm calculating equivalent radius. So and then it is going to be like that I am injecting something in order to clean the well. Now I'm making enlarging drainage radius, so I'm increasing well radius, well equivalent rate. Instead of that, I have another presentation when I am making 3 fractures, and then I'm putting half length, and I'm plotting equivalent 1 fracture half length. That means instead of having 3 fractures, I will have 1 fracture, which is also going to be transversal, but with a larger half length. That is LEF. So I have REF and LEF. So you can see here that by calculating that I'm able to make that I have seen that I'm here now doing the following. I'm using transversal fractures, but also longitudinal. So the first one, the first drawing above, is related to the equivalent radius. The last 2, the second one, is related to the 3 longitudinal fractures. So I have like this longitudinal 3 fractures, and at one of the bottom is related on the 3 perpendicular fractures. And that is based on the formulas above. This whole paper is published in detail, and these formulas are very valuable if someone wants to use also fast screening analysis. Instead of emulating that he has, let's say, 3 fractures, he put one fracture half length, or he increased the radius, which is going to be emulating 3 transversal fracture production or longitudinal fracture. So this would be all for this part. The paper number SP 12826. Okay. So now I suggest maybe just give me 2 minutes, then I change I'm going to stop to sharing the screen. Oh, what is now? Hello, everyone. Just to see. How one study look in the North Sea, because otherwise we are all tired because then tomorrow we will start with another studies. But let me show. So Maersk Oil is the company where I worked just before I came to Ukraine, in Denmark. This is almost like a Danish shell company. Now I think that they are even merged with Total, I think. So you see they have a drilling company which is drilling all the wells in Norway and also Denmark and UK. So these are the Halfdan field and Dan field. You see here, these wells may be several kilometers with 24 fractures on it. Can you imagine that you have about 40 horizontal multi-fructured wells and then you are producing? How you are going to simulate that? It is impossible. Because of course, it is possible with intersect, but otherwise with a simple simulator, it's just impossible. Because you have to have, such a gridding around each. We will see tomorrow about this gridding and what you have to do in order to make production proper. So basically, the only way, so I got the problem, and the problem was the following. I have 2 horizontal wells, and I want to have the one is a water injection well, and another well is oil producer. I want to have from these 20 fractures, 1 sector, and to make to solve recovery analytically. Can you imagine your manager is coming to you and say like this, hello guys, I will give you certain time. In that time, I want to have from that, I have a horizontal well with a fracture. And then I have another horizontal well with a fracture, transversal fracture. Around this fracture, I made the sector model. And then I want to make, let's say, otherwise you're not going to. So I have one model, another color. Okay, this is my 1 fracture. That is my well, and then 1 fracture. And then I have another fracture. Well, that is like this, okay? And then I have very many fractures up to here. This is 1 well, and that is another well. It has a lot of fracture like this. So now I want to have this model here. I want you to, this here is going to be water well, injecting water, and here I am producing oil. Okay? So now I'm asking you, you have to find the injection rate of the water at a certain time. And then you have to make analytically recovery of water injection or gas injection in that way. Do it. UGV reservoirs, okay? Do it. Okay, this is the one problem which I was also facing when I was. So now just to go. What is now? I'm going to be again black with this. I have to put it here.
Branimir.
Yes.
Yep. I'm sorry. Let us leave these tasks for all the guys for tomorrow. We confirm that tomorrow we will continue at 4 o'clock, as you asked me, because today after 15 minutes we will have the next lecture. With the lecture.
Yeah. Okay.
Okay.
But
for today, I guess.
This is just for you to. This was I finished with this because this was my note.
Okay.
I put that as a to think about. That's another lecture anyhow. It is not so easy task.
Okay. So,
and then in this case we stop here, and then tomorrow I will start. How we say? Is it at 4 o'clock or 6 o'clock?
At 4 o'clock. At 4 p.m.
4 o'clock. Excellent.
Yeah.
Excellent.
Yeah.
Okay.
It will be exactly at 4 o'clock. I have the confirmation about the 4 o'clock, and we will change the lecture from France to the morning. Okay. So.
Okay, but thank you. And what is the next lecture?
The next lecture will be about hydrofracturing. This will be held by the guy from Russia who was service company for Detect company when they performed hydrofracturing at their wells.
Oh, interesting. Okay.
So you can join us.
Yeah. Okay. But how it is to join? How that is to make?
I will send you the link to your mailbox. Okay, and you can join us.
Okay. Thank you very much. Okay. Cheers. Okay.
Yes.
Bye.
Thank you guys for your attention. We will be waiting for you at 2 o'clock with a hydrofracturing overview, fundamentals and analysis.